Right, in this video, we're going to talk about the idea of a vector field being conservative. We have a definition for that. And if so, the idea of evaluating line integrals, that they can be path independent, meaning you can get the same answer no matter what path you take. So let's just start with hopefully you watched the previous video. We were talking about evaluating line integrals. And if I have this vector field and I want to evaluate, this could be thought of as circulation or work. As you might recall, they have the same formula. Probably here I'm going to think of it in terms of work, but it doesn't really matter. It's the same formula. So say I want to calculate the work in pushing a particle from -1, 1 to 1, 1 with this vector force field. And so to do that, we have to parameterize a path. And so this is a parabola. The equation is y equals x squared. So the simplest way to do it is to just let x be t. And so therefore y has to be t squared. And if x is t, you can see that t should go from -1 to 1. This is x, this is y. So we're going to need dr dt, so that's the derivative. That's just going to be 1. This will be 2t. And along this curve, my function f, which is 3x squared y squared, will be, I'm just putting in x and y here, it's going to be 3t squared t squared squared. And then for y, it'll be 2t cubed times t squared, because I'm putting that in for y. So if I simplify this, this will be 3t to the 6th, and this will be 2t to the 5th. So then I can evaluate my integral f dotted with dr. My limits of integration, we saw earlier, we're going to be from -1 to 1. My f is 3t to the 6th, 2t to the 5th, dotted with dr, which is 1 to t. If I do the dot product, that's 3t to the 6th times 1 plus 2t to the 5th times 2t is going to be 4t to the 6th. Oh, and that just combines 7t to the 6th. That's a nice antiderivative. That's t to the 7th. If I evaluate it from 1 to -1, I'm going to get 1 minus -1, which is going to give me an answer of 2. So let's use that same vector field, but let's now compute the integral of f dotted with dr along a different path. This time we're just going to go straight from -1, 1 to 1, 1. So that parameterization, if I want to parameterize that, I can, t is changing. There's more than one way to do it. I'm just going to say that we're going to just have x be t, y is always 1. And if x is t, then once again, I could just have x or t just go from -1 to 1. There's other ways to do it. You could parameterize this from 0 to 1, and you'd have a different formula, but it should still give you the same answer. With this parameterization, dr dt is going to be 1, and this will be 0 when I take the partial derivative. This is x, this is y. My function, which was up at the top, is 3x squared y squared, so it'll be 3t squared times y squared, which is 1 squared, so that's just 1. And then for y, it's going to be 2t cubed. It was 2x cubed times y, so it's going to be 2t cubed times 1. So that's 3t squared, 2t cubed. And so to now dot those two, do the integral. I'm going to have the integral of f 3t squared 2t cubed dotted with dr, which was 1, 0. And it'll be from -1 to 1 again. That was our parameterization. Notice this time my dot product, I just get 3t squared, and then this is just 0. 2t cubed times 0. So my antiderivative there is t cubed evaluated from 1 to -1. 1 cubed minus -1. 1 minus -1 gives me also 2. So what you hopefully picked up on is I'm getting the same answer for this integral. We did it, the integral of f dotted with dr along the parabola y equals x squared. We got an answer of 2. And we just did the straight line parameterization from here to here, and we got an answer of 2 as well. I know that could be a fluke. We only did 2 paths. But if you tried a different parameterization from -1 to 1, 1, you would find out that you would get the same exact answer no matter what path you take. And this is only going to happen. It's a property of the vector field. So this particular vector field that we used that seemed to be path independent, that's where that term comes from, right? We got the same answer on 2 different paths. This is called a conservative vector field. Because it is the, okay, so, well, I'll tell you what it is and then we'll work backwards. If you go back to like 21C kind of stuff, this is the gradient of a special scalar function, which we call the potential function. Here's what I mean by that. If I gave you the function, it's probably easier to think backwards at the beginning here. If I gave you a function of x and y, which was x cubed y squared, and I asked you to find the gradient of that function, remember that the gradient is a vector, which is made up of your partial derivative with respect to x and your partial derivative with respect to y. And sure enough, what's the partial derivative of this with respect to x? It's 3x squared y. Partial derivative of this with respect to y is 2x cubed y, which is exactly the same vector field we were working with. So that makes f a conservative vector field because it's the gradient of a scalar function. So if f is a conservative vector field, as we saw, the work done in moving a particle from A to B, in other words, the integral of f dotted with dr, that could also be interpreted as circulation, right? Or flow. You're going to get the same answer no matter what path you take, which is kind of interesting. I'm sure we did on a previous video, we calculated the circulation between 2 points along different paths and we got different answers. You might want to go back and convince yourself that this is not always true. You're not always going to get the same answer for this line integral if you take 2 different paths from A to B. But in this case, this would explain why we got the same answer for using 2 different paths. It's because f was a conservative vector field. And in fact, here's another neat thing about if you're working with a conservative vector field f, we could actually compute that integral, line integral of f dot dr more simply using what we call the fundamental theorem of line integrals. So if you have a line integral, you're doing f dot dr, and f happens to be conservative, remember what that means. That means, here I'm going to take an intermediate step, that means you're trying to compute an integral of the gradient of f times dr. And when it reminds you of the fundamental theorem of calculus from 21b. If you're taking remember the gradient is derivatives, right? You're taking derivatives of your function. The antiderivative of the derivative just cancels it out. And it's just going to leave you with your function of whatever x and y. And you would just plug in the top limit and the bottom limit, f of b minus f of a. And that hopefully reminds you of almost a direct parallel to the fundamental theorem of calculus in 21b. might want to go and look that up and see the similarities. So here's what I mean by that. In the last example we did, here was our vector field, and we now know it was the gradient of a scalar function, that function being x cubed y squared. We wanted to do the integral from the point -1, 1 to 1, 1 of f dotted with dr. But according to this, what we could do is just know that that is our potential function, x cubed y squared. And this says evaluate it from b to a. So I'm going to evaluate this from 1, 1, 1 to -1, 1. And if I plug in 1 there for both x and y, I end up getting 1. If I plug in -1 for x, 1 for y, I get -1. 1 minus -1 gives me my answer of 2, which if you go back, that's the same answer we got when we computed the line integral along the parabola. We got 2. When we computed the line integral as a straight line, we ended up getting 2. And this says you will always get 2, no matter what path you take. So hopefully, as you can see, if you're working with a conservative vector field, doing the problem this way, evaluating the line integral this way, could be very simple, very, very easy. But not all vector fields are conservative. And so how are we going to know if a field we're working with is conservative? There is a test for it. This is the one that's given in the book. If I define my vector field as, let's go 3D, M, N, and P, then you would need to check that all 6 of these, well, 3 pairs, there we go, of partial derivatives are equal to each other. This one, and this one. It turns out for a 2D field, you won't, because you don't have a P value, right? We just have a field of M and N. You just need to check that these 2 partial derivatives are equal to each other. But for a 3D vector field, you would need to show that all 3 of these are equal to each other. And to me, this is a lot. I have a hard time remembering all of these right here. And even though this comes up later on in section 16.7, once you learn this idea in 16.7, you can use the idea of a curl to tell if a vector field is conservative. So even though it's coming later on, I'm still going to introduce it, and a lot of times professors will anyhow, even before we get to section 16.7. So here's the idea of the curl. It's a property of a vector field. If I'm going to define this notation, which kind of looks like the gradient notation, but I don't attach an F to it, and this is read as just del. So if I define del to be a vector that's just made up of the partial derivative of whatever I'm dealing with respect to x, y, and z, then we're going to define the curl of F. This is a property of the vector field, is del crossed with F. What that essentially measures, we'll do this in a second here, but it measures, you've got a vector field at every point in your vector field, it measures essentially the circulation at every single point. So the tendency for something to move around this circle. When you do a curl with a vector field that's just 2D, it's going to generate a vector that's pointing straight up. And the magnitude of that vector measures the rate of rotation, that the tendency for this vector field to push something around a circle. All right, so if we compute that for a general function, del cross F, so we're going to do partial with respect to x, partial with respect to y, partial with respect to z, crossed with F, which we're going to define to be M, N, and P. To do this determinant, remember you block out the row and column. So we're going to have the partial of P with respect to y minus the partial of N with respect to z. For the middle one, remember you always get a minus sign. I'm going to put this up here. That's going to be minus, and then what do you get? You get the partial of P with respect to x minus the partial of M with respect to z. And I put it up here because if I were to distribute this, what I would see is I could put this one first. It would be the partial of m with respect to z. Wait, is that right? Give me a second here. Yeah, minus this, and I could call this plus. There we go. That's what I was missing. Minus the partial of p with respect to x. Now we're good, because that would be positive. When I distribute this would be minus. And then finally for the k component, that's going to be partial of n with respect to x minus the partial of m with respect to y. And so I think here I was just going to write this in vector form. So this is partial p with respect to n minus partial with respect to y, partial n with respect to z, partial m with respect to z minus partial p with respect to x, partial n with respect to x minus partial m with respect to y. And here's our definition. If the curl of a vector field is 0, then f is conservative. Then f is conservative. And that can be used. That's where these things come from. If I set this, that means all three of these have to be 0. So if this is equal to 0, what does that mean? It means the partial of p with respect to y should be equal to the partial of n with respect to z. If this is equal to 0, it means the partial of m with respect to z should equal the partial of p with respect to x. And then this one, partial of n with respect to x should equal the partial of m with respect to y, which are the same. Those are the requirements that you're given in the book at the top here. That's how you tell if it's conservative, but that's where it's coming from. They don't tell you this yet in chapter 16.3, but it's coming because the curl of our vector field must be equal to 0 for it to be conservative. And when you do the cross product, you end up with these partial derivatives, which would have to be 0, which means these partial derivatives should be equal to each other. So you can memorize these, of course. You can know how to compute the curl as a vector and then just insist that all three of these have to be 0 to get to these if you forget. So that's one nice thing. If you forget, just set the curl equal to 0. So now we have a way that we can quickly tell if a field is conservative. And if it is, then it should be the gradient of a potential function, which we can find. Now, this is a 2D field. And recall, for a 2D field, this is what I would call m, this is n. You only need to check, so back on this page, that the partial of n with respect to x is equal to the partial of m with respect to y. So let's just check that out. Partial of n with respect to x should equal the partial of m with respect to y. If I compute my partial of m with respect to y, this one right here, this one with respect to y, x is constant, so that's 0. I'm going to get, that'll stay there. I'm going to get 2y times 9x squared. So I'm going to get 18x squared y. Partial of n with respect to x. Y is constant now. That'll be 18x squared times y. And since y is constant, that'll be 0. So yes, these are the same. So f is conservative. Now, if f is conservative, then it should be the gradient of a function, a scalar function, which we call the potential function. So now we want to find it. So I started to write down here, remember that f is the gradient of some function of x and y. Our f that we had was 4x cubed plus 9x squared y squared, and then 6x cubed y plus 6y to the 5th. Now I take a slightly different approach from the book. If you read the book on how they do this, they integrate, then they take the derivative, then they integrate again. Here's the way I think of it. This right here should be the partial derivative of whatever my function is with respect to x, and this is my partial derivative with respect to y. So if f sub x is equal to 4x cubed plus 9x squared y squared, then my, okay, I put this in quotes, for now, I'm going to call this f, which is my potential function, should be the antiderivative of this, right? 4x cubed plus 9x squared y squared with respect to x. So what would that give me? Well, the antiderivative of this with respect to x, this is already x, that's x to the fourth. And if I treat y as a constant, this would integrate to 3x cubed y squared. But now, normally when we integrate, we have to acknowledge there's some constant, of course. But because I'm integrating with respect to x, I also have to acknowledge that there could be some function of y hanging out there, right? Because if this was strictly a function of y, if I take the partial derivative, it wouldn't have showed up here. And then, of course, just some regular old constant number. Now, the book here has you take the derivative of this, but I find that confusing. I'm just going to do this. If I integrate this with respect to x, I get that. So now let's try integrating. If f sub y is 6x cubed y plus 6y to the fifth, then my, for now, temporary potential function or possible potential function, if I integrate this with respect to y, x is constant, so this will be 6x cubed y squared over 2. The 2 is going to cancel. I'm going to end up with 3x cubed y squared. 6y to the fifth with respect to y is just going to be y to the sixth. But similar to what I did here, if I integrate this purely with respect to y, I have to acknowledge there could have been some function of x just sitting out there by itself, whose derivative would have been 0 plus some constant. So then the idea is, you can tell now, when I integrated with respect to x, I got this, and I got some pure function of y. When I integrated with respect to y, I got this. Well, notice these two show up, so that should definitely be part of my vector, my potential function. But what does that say? Well, this g of y must have been this, huh? That must have been y to the sixth, and it makes sense why it didn't show up here, because that was a constant, right? If I took the derivative, it would be 0. And likewise, this function of x here must have been this function, a strict function of x. So essentially then for my potential function, I just put everything together that I found, as long as it showed up in one or the other. So I'll start with the x to the fourth. 3x cubed y squared showed up in both of them, but I only need to put it once. And then y to the sixth plus some constant. Just put everything that shows up. Now I can prove this is, you can work backwards, right? You could take the partial of this with respect to x and you'll see you get that. You could take the partial of this with respect to y and you'll see you get that. So it is a potential function. Right? How about this one? Now we have a 3D vector field. So I have m, n, and p, and I already got it written down here. So what I need to see is I need to check to see if the partial of p with respect to y equals, I'll put a question mark, the partial of n with respect to z. Well, the partial of p with respect to y is 0, right? There is no y in there. The partial of n with respect to z, y is a constant, is going to be y e to the z And what's nice about this particular one is the minute that one fails, I don't need to bother checking the rest of them. This cannot be conservative, not conservative. It has to satisfy all of them. So if this one was true, but the middle one was not true, then it's not conservative as well, right? It fails either of those. Okay, how about 3 here? Once again, we have an M, N, and a P. So we'll start the same way. Let's see if the partial of P with respect to Y equals the partial of N with respect to Z. Partial of P with respect to Y, once again, is 0. There is no Y in there. And the partial of N with respect to Z is also 0. So that checks out. The second thing I have to check is whether my partial of M with respect to Z is equal to the partial of P with respect to X. M with respect to Z, looks like I'm going to have to use a product rule here, right? So I'm going to have to do the derivative of the first is 1 times cosine of xz plus z. Derivative of cosine of stuff is negative sine of xz times the derivative of the inside with respect to z, which would just be x. I need to see if that's equal to the partial of P with respect to X. Once again, a product rule. Leave the first one there. Derivative of the first, sorry, 1 times cosine of xz plus x, and the derivative of cosine of xz, we just saw it right there, is negative sine xz times z this time, though, because I'm doing it with respect to x. But if you take a careful look, right, this matches up with this matches up with this, they are equal. And then finally, I have to check to see if the partial of n with respect to x is equal to the partial of m with respect to y. Oh, there we go. Partial of n with respect to x is 0. Partial of m with respect to y is also 0. So it satisfies all 3 of these. So yes, this is conservative. Okay, but what do we now need to do now? They said if it was a conservative field, we need to find the potential function. So let's try that. So then if what should be true, so now I'll make this a little quicker. This should be, for some potential function, this should be the partial of that with respect to x. This should be my partial of f with respect to y. This should be my partial of my potential function with respect to z. So what I'm going to do is integrate this with respect to x, integrate this with respect to y, integrate this with respect to z, and see what I get. So if f sub x is z cosine xz, then I'll do the same thing, quote unquote f. So I'm integrating, and now I'm just going to do it in my head. I'm integrating with respect to x. So z's constant, antiderivative of cosine of xz would be sine of xz over z. So the z's are going to cancel. I'm just going to get sine of xz. Check for yourself if you take the partial of this with respect to x that you get this. But now here's the deal. On the previous one, we were just doing a 2D version. I just integrated with respect to x where I'm treating both y and z as a constant. So I have to acknowledge that there could be some function of y and z hanging out there, plus some numerical constant c. If my f of y was just e to the y, then my f, if I integrate that with respect to y, is e to the y plus some possible function of x and z. So I would have been holding those constant. And then finally, if f sub z is x cosine of xz, integrating this with respect to z, x will stay there, but it's going to be sine of xz over x, so it's going to be sine of xz plus, let's see, gh, how about j of yz? So what do we then know? Well, sine of xz showed up in both of these, so that's definitely part of my vector function, and so did e to the y. And in fact, e to the y could be an explanation for that, right? That's a function of, well, just y. And that could also explain this one right here. So then my potential function is sine of xz plus e to the y plus some constant. And again, if you want to prove that that's true, start taking your partial derivatives and you should get these answers. Okay, I'm going to use this example to recall, okay, why are potential functions so useful? There's that idea of path independence and the fundamental theorem of line integrals, right? Because this is a conservative field, if I want to integrate f dot dr of this very same function from 0, 0, 0 to 1, 1, 1 along these crazy paths here, I know a couple of things. I know, number one, if I didn't recognize, if I knew it was a potential function, I don't really need to do 3 integrals. I could just, for example, set up one integral from the origin to here along a straight line, because it's path independent, right? F is a conservative field. It doesn't matter what path I take. But even better than that, I don't even have to really do a line integral, because according to the fundamental theorem of line integrals, it says I can just evaluate my potential function at the endpoints. So I'll say, since f is conservative, we can just do this line integral of f dotted with dr is just my potential function f of x, y, z evaluated from, well, my final point, which was 1, 1, 1, to my beginning point, which was 0, 0, 0. So the value of all 3 of those, if I were to do them individually, I would just end up with my potential function, which recall was sine of xz plus e to the y. I don't really need the constant because it's going to drop out. And if I put in 1 and 1, I'm going to get the sine of 1 plus e to the 1 plus, well, plus some constant c, but then I'm going to get minus sine of 0, which is 0, plus e to the 0, which is 1, plus c. The c's are going to cancel out, so I'm just going to end up with sine of 1 plus e minus 1. Super, super useful, right? I just need to evaluate my potential function at my endpoints. I don't even have to do the line integrals, because f is a conservative field. One final cool note on this, that if f is a conservative field and it comes down to just evaluating the potential function at its endpoints, what if you had a closed loop? What if your parameterization was, you know, some kind of curve like this, and you began and ended at the same point? You know, say it was 1, 2, 3, and you had some curve that took you around all the way around here. Because if it was a conservative field, you would just find the potential function and you would evaluate it. You would evaluate your potential function from 1, 2, 3, to 1, 2, 3. And what's going to happen if you plug in 1, 2, 3 minus the value of the function at 1, 2, 3, you are going to get 0. So if f is a conservative field, the line integral all the way around a closed curve will always come out to be 0 for every closed curve 0. What better than to see that really in action here is to just do an example. So here's my field f. I want to evaluate this for the circle cosine t sine t from 0 to 2 pi. That's just your unit circle. We've worked with that one plenty of times. So it looks like I'm starting right here from 0 to 2 pi. So I'm starting at the point 1, 0, and we're going around the circle. That's how the parameterization would describe that circle. So if this is a conservative field, then I know that that is going to come out to be 0. But just to prove it, let's do the line integral directly, right? So we're going to actually evaluate the integral here. So this is x, this is y. So on r of t, what is f? F will be 2 cosine t, y will be 3 sine squared t. And of course, dr dt, just my derivative is going to be negative sine t cosine t. So therefore, my integral would be the integral from 0 to 2 pi. Let's just do the dot product, f dot dr. So I'd end up with this times this, so negative 2 sine t cosine t plus this times this, 3 sine squared t cosine t. Whoops, that's not a, should be a dt. Hopefully this isn't too bad, right? If I let this be u, that would be du. So that's just going to be that's just going to be u du. And so that's u squared over 2. So the 2's will cancel. So this is just going to be negative sine squared. This first one. And I'm seeing a similar thing here. If I let u equal sine of t squared, there's your du. So this looks like 3u squared du. It's going to integrate to u cubed. So plugging back in, this will be sine cubed. If I go from 2 pi to 0, sine of 2 pi is 0 plus 0. Plug in the 0, I get 0 plus 0. I get an answer of 0. Which is exactly what would be true if we can show that f is a conservative. Then we know that it's a closed loop. The answer should have been 0. So remember my field was 2x 3y squared. That's my m, that's my n. And if you recall from earlier, to show that it's conservative, to be conservative, we need to show that the partial of m with respect to y is equal to the partial of n with respect to x. Partial of m with respect to y is 0. Partial of m with respect to x is also 0. So it is a conservative field. And in fact, you could probably just refer to, because it's the closed loop property, because you're going from all the way around the circle, that the line integral of f dot dr should be 0. But we could even prove it, because what is my potential function? Well, if this is f sub x, and you integrate that with respect to x, you get x squared. If this is f sub y, and you integrate that with respect to y, you get y cubed plus some constant. So the integral of f dot dr would be equal to my potential function x squared plus y cubed, sorry, evaluated from where I started on the circle, which was 1, 0 to 1, 0. Of course, I'm going to get 0. All right. This was a rather long video, but a lot of things to talk about. Hopefully this makes sense. Let me know if you have any questions.